Thank you everyone, good morning, and thank you for showing up today. So I will be presenting my master thesis research which I conducted back in 2018 on a project of ArcelorMittal mining company in collaboration with the Georesources Lab from the University of Lorraine. So it was mainly focused on investigating the effect of process water finite salinity on flotation performance in a two-phase and three-phase system. So I would start off with the research motivation, that what prompted us to go for this research. As we all know that presently and even in the future we will be struggling with the water around the world, and particularly in mining where we use big quantities of water. So there is going to be a water war in the future. It would be shifted from black war towards the water wars. So a study by Hatch in 2012 shows that in future, and even if you look at that dot point in the middle where we are at the moment, there is going to be like a big gap between the water availability and water demand. So when we need that much water, so obviously we need to focus more and more on finding another sources to operate our mining operations and to keep them going. On the other hand, whenever we go for the mining operations, so there are always very strict environmental constraints. So environmental impact agencies say that mining operations kill flora and fauna when we drain off the water, so that water percolates into the water table, and then that water is not drinkable anymore. So that puts mining companies in a position to find some alternative solution or to treat that water. So which is why mining companies recently started to focus more and more on reusing their processed water. So these were mainly the two research motivations which prompted us to go for this study. So an attempt was this, keeping in view that problem, an attempt was done by ArcelorMittal Krivera, ArcelorMittal mining company at their Krivera operations, which are located in Ukraine. So what they did, they wanted to upgrade their magnetite concentrate using the processed water. Why they wanted to upgrade that? Because at the moment they are getting magnetite concentrate with significant amount of silica in it, which is not accepted in the market. So there is in the recent decades, there is a reverse cationic flotation that became quite famous because of its application for upgrading the concentrate quality, and particularly for the removal of silica. So that is quite efficient and low cost. So when they performed that process on their magnetite concentrate, they saw that they didn't go successful when they used processed water. So why that happened? So there came my research in. So we wanted to investigate that fact. So the processed water of that place was tested over a time from 2014, 6 months, to 15th of the 7th month, 2015, a couple of times periodically the water was tested, and we found that there were the presence of chlorine, sulfates, magnesium, similarly calcium ions present in that water. So at their research center, which was based in Metz, France, they performed some batch flotation studies, and they saw when they are using the processed water from Metz is basically the name of city, don't confuse with that. So when they use that process tap water, so efficiently they can remove the silica down to 2%. However, when they use the processed water along with different type of collectors, they cannot isolate the silica from the magnetite concentrate. So I would like to give you first a bit of the background on the geology of the deposit as well, so that you know that from where this is coming and what kind of the associated minerals are there for this magnetite concentrate. So basically this deposit is located at the southeast of Ukraine, at the border of the two geological units, which is Kirovograd and Dnepr. And these iron ores, magnetite iron ores, they are basically associated with the banded formation, and with an average grade of around 36%. And the main minerals are magnetite and magnetite silicates. And if you so this is mainly the Krivera complex, and a section is taken from south to north, and we have different type of mines operating in this area, because we have got the magnetites and magnetite silicate deposits here, which are of high grade. So our mine is operating somewhere here. Moving forward, so here is a mineralogical study. So MLA was performed at the different size ranges, and if you look at that, we would see that we have a significant amount of magnetite that is existing at the quite fine size fraction between the 38 to 75 micrometer. And as we move upward to as we increase the size of the particles, so we see the amount of magnetite is decreasing in the coarser fractions, and alongside the increase in the silica content. But even the size fraction where we are working, that is where we have the high concentration of magnetite, we see that we have 8% of the silica, and then silica is almost consistent in all the size fractions. So that's why we wanted to go for upgrading magnetite concentrate, because it was quite low. So this is the current operational flow sheet of the plant. So we have a head grade of iron that is around 36%, and silica around 44%. So we have 3 stages of milling at each stage, followed by a classification unit. As in the first one, it's the spiral classifier, while in the second and third stage, these are the cyclones. And then the product from spiral classifier is then goes to magnetic separation, and then which follows again in the three stages. It follows this route, and finally we get a concentrate with a magnetite concentrate, which has a grade of 66% around and associated 8% silica. But this 8% silica is not accepted in the market. So the research objective was to investigate why is that all happening when we use processed water. Why are we not able to recover silica from the magnetite concentrate? And it has to be done in 2 phases, because there are a myriad of studies that has been done to investigate the effect of salts, but they were just specific either to a batch scale level or to just specific to one-phase system, or two-phase system. Not there was not a combined study and covering a fundamental study that had been done before. So I wanted to say how these salts affect the bubble-bubble interaction, that is basically the two-phase system. I will be talking about that now in detail, and how is it going to affect the three phases, when you have solid, when you have liquid, and when you have gas. So it was presumed that it could potentially happen because of the 2 reasons. So salt can affect either the interaction of bubbles with each other, or it could be either due to the adsorption of those salts on the we were using cationic collector when we were performing cationic flotation. We use cationic collector because silica has got a negative surface charge, and we use cationic collector to withdraw that silica from the concentrate. But when there is a processed water, so there are ions, as I told you before. So there is going to be a complex reaction happening between that. So I wanted to investigate that as well. So to study the first phenomena, the fully automated pilot scale flotation column was used to see the effect of salinity on bubble-bubble interaction. That was in the 2 phase. And to investigate the effect of processed water salinity on the 3 phases, some fundamental studies were performed where microflotation was done on pure quartz, because we were interested more in the quartz, and then some contact angle measurements followed by zeta potential measurements. So the question is, does water salinity promote flotation or not? Yes, it does. So what happens, usually water salinity is favorable in reducing the coalescence and thus the bubble size. So what is coalescence? In simple words, coalescence is when you have 2 bubbles inside a system, inside a flotation system, and due to the hydrodynamic conditions inside, because you have impellers which create hydrodynamic conditions inside. So when these 2 bubbles come closer, so there is a chance that if you look here, these 2 bubbles are approaching each other inside this liquid medium, and these are basically gas. bubbles. So when they approach, there is a very thin layer. So they are what is happening is they're trying to drain off the liquid boundary between them. And a moment comes like when you completely drain this liquid boundary or a very thin film of liquid, and these two smaller bubbles becomes one bigger bubble. So so when you have like a bigger bubble, it affects your flotation performance. So this is called the coalescence phenomena. So what happens, like if you have salts inside in your water, so it is going to reduce that effect. So it means it then will promote your flotation. So on the other hand, these salts also reduces your bubble size. Research shows that. So here you have Gordon in 1957 showed that like the probability of collision of bubbles is inversely proportional to the bubble size. If you have smaller bubble size, then you will be having more probability of collision, and then there will be more chances of the particles to be attached to the bubble surface, and then it will promote flotation. However, that's not always the case. Research also shows that salinity restricts the flotation performance as well. How that has got negative effects. So sulfates and carbonates hydrolyze at alkaline pH and precipitates as hydrophilic metal hydroxides. And similarly, there are always like some calcium and magnesium ion that modulate the surface properties of molybdenite and affect molybdenite quartz separation. These are just like some studies that have been done in the past, and I have just collected to see that it can negatively affect your flotation performance as well. And similarly, presence of metallic cations hinder the flotation of pyrochlore. So this was very interesting study that was done by Craig back in 1993 to see the effect of ions on the bubble coalescence. So what he did, so he categorized anions and cations, and he gave a nomenclature that if you have alpha or beta presence of ions in your system, then it's going to inhibit coalescence. So it means like it's gonna improve flotation. And if it's a cross relation like alpha beta and beta alpha, then it's no good for your flotation system. So if you just look at sodium on the top right, and if you get down and if you compare it with the anion like fluoride, and you see like you have a tick sign which corresponds to inhibit coalescence. So it means that sodium chloride is inhibiting coalescence according to literature, so it should improve the flotation. And similarly for the other ions combinations. So to investigate the effect of process water salinity on the bubble-bubble interaction, so as I told you before that I use fully automated flotation column that was based in that is installed in France at the Georesources lab. So it is mainly like a 5-meter flotation column. So you have a feed tank here, and feed is introduced here at this point. So you can see the corresponding parameters, and then you have a liquid recirculation, so that all the liquid that is recirculated goes back to the feed tank. So for each experiment I was using 40 liters of the water. So what I did, like I prepared synthetic solution because the availability of water was not with me. So what I did, like I knew the composition of water which I showed you in my earlier slides. So I made synthetic water, like 40 liters synthetic water for each experiment to conduct that study, and then I performed those experiments. And this was, but before going forward to make the synthetic water, I had to check on the salinity or the amount of salt which are already present in my water where I was performing experiment. So it was non-C, so I did some analytical studies on that, and I got the report, and these were the presence of ions I was interested in to study. And yeah, so there were two pressure sensors attached, so which were basically meaning the value of pressure. So where I was using the value of pressure, I was using that value of difference in pressure to measure the superficial gas holdup. So what is gas holdup? Basically gas holdup is the volumetric fraction of the displaced liquid inside your system, inside your flotation system. So what happens basically when you have a flotation column, so it's fully loaded with the 40 liter of the fluid, and then you have a sparger, which in this case is here. So sparger is like we have a recirculated liquid plus a gas, a flow rate of the gas, which mix together and then introduced through a perforated tube into the column, so which create bubbles inside. And here, this is the zone, that's where we were measuring the uniform distribution of the bubbles. So how was we measuring that? We was measuring that through the drift flux method. So there are different kind of methods, but the one I was interested in was drift flux method, because I didn't want to disturb the hydrodynamic condition of the system. So yeah, the rest is like here, the gas flow rate, which is reported in form of superficial gas velocity. So this is just the gas dispersion characterization. Yeah, as I told you before, the gas holdup is the volumetric fraction of the displaced liquid, and once you have calculated your difference in pressure, so using this formula you can calculate the gas holdup, so which is something we will be investigating further, that will help us to see how is it going to, this is basically a parameter characterization parameter to study the effect of salts on the bubble-bubble interaction. And this is the bubble diameter then utilizes the value of gas holdup, is then used to calculate the bubble diameter, average bubble diameter. So when I say average bubble diameter, so the people who are working in flotation, they would be knowing, like I'm talking about Sauter diameter, that is D32. And to calculate that, drift flux method was used. So drift flux method have different kind of algorithms. It has been modified from time to time, but the one that I used was one from my professor, Filipov. He modified it empirically a bit in 1996, and this is the one, like the value that I was getting for the bubble size and for the gas holdup from my software in the computer. It was using this algorithm. So what it does basically, it takes into account the slip gas velocity, which further takes into account like the terminal velocity of the bubbles, as well as the gas holdup, and then this parameter m, which uses Reynolds numbers of the bubble, and then calculating this USG value, which is the terminal gas velocity, and then this terminal gas velocity is used for the creation of bubble diameter using this algorithm. On the other hand, I had to investigate the effect of the salts on the quart surface. So the collector that I used was cationic collector, and that was dodecyl amine. It could be anyone, but I used dodecyl amine. So to investigate that effect, so first I did microflotation. So microflotation it's a small scale flotation that you can see in this picture. It's a very small flotation cell, and it's performed in a volume of 350 milliliter of the pure deionized water. And the size fraction that I used for the experiment was pure quartz from 53 to 88 micron meter. It's a bit as we saw, like we were isolating magnetite from silica at around 48 micron, as we saw in the flow sheet. But here I was able to, like, I had a distribution from 53 to 88 micron in my feed, so that's what I used. So the gas used was nitrogen, and yeah, conditioning time, yeah. And to support those results from microflotation, I did some contact angle measurement. That's a really fundamental study to see that, okay, whatever I'm getting in my microflotation, why is that happening? So to support that result, I did some microflotation using a drop shape analyzer, state-of-the-art equipment. It's a very good one. And the pure quartz sample was prepared, and every time to use that, it was like polished with a silicon carbide sandpaper with the pore sizes, as you see, 800 to 2400. and the fitting method that was used for the contact angle measurement was Young Laplace. And the sample was washed after each experiment with ethanol followed by acetone and then distilled water. After that, finally, to say that okay, our minerals have surface charges on them, how our cations or anions which we are introducing to our system through process water, they are going to affect or disturb our surface charge of the mineral. So in this case, we were interested in quartz because we were performing reverse cationic flotation. So we were seeing that okay, when we add salt individually or as a mixture, how are they going to affect that? So we did zeta potential measurements and zeta compact was used, and the size fraction which was used for the zeta potential measurement was less than 5 micrometers, so it was pure quartz. So that I obtained by through tungsten mill plus pestle agate and mortar, and then I isolated that through sedimentation using the Stokes law, and that calculation it was really difficult. So now heading towards the results and discussion. So these are the results for the first phenomena, that is again to investigate the effect of water salinity on the bubble-bubble interaction. So it was seen that if you plot gas holdup versus superficial gas velocity, so superficial gas velocity, I would recall, it's your gas flow rate divided by cross-sectional area of the column. So, and the gas holdup, again, I would recall it as well. So it's the displaced volumetric fraction when you introduce gas. So it was seen that they have got like a linear relationship for different type of salts. So first of all, Nancy type water was used without using any salt. So it was seen that a very linear relationship holds, and then the other salt concentrations based on the process water composition that I got after chemical analysis or from the data from the company, again saw that even if we have the presence of salt like calcium, magnesium, sodium and potassium chloride, it doesn't affect the value of gas holdup significantly. However, sodium sulfate, it was seen that comparatively it has a bit larger effect, and if you move further and you use the sodium chloride concentration present in the salt water, and you see it will give you like a very high effect on your bubble. Sorry. Also, I also used one frother that's not here in the legend, but this line is basically for the frother. So this study shows that if you use higher concentrations of sodium chloride, let's say 0.3 molar, so this is not basically my composition from the saline water. This is just a random higher concentration, but is it almost equivalent to the salinity, like the concentration from seawater. So there was also an aim in our head, like, okay, the water scarcity issue could also be managed. What if we don't use process water? We can go for the seawater as well, because 97% of the water in this globally is from the sea. So it was tested that okay, if we use high concentration of sodium chloride, we can somehow get closer to, we can mimic the effect of frother basically. If we further increase, and the trend shows that almost like we will get closer to frother. Now, how is my superficial gas velocity affecting bubble size? Based on the presence of the salts. So again, it was the linear trend was like almost linear trend was seen, but it was contrary to the results from the gas holdup. So in the gas holdup we saw we had like a linear trend, it was increasing, but in this case when you have different type of salts, it shows you decreasing trend. And the reason I'm comparing this superficial gas velocity, I'm doing the study at different values of superficial gas velocities for the sake for this set, because there are different type of flows inside your system when you're performing flotation. So here there is a figure, so it could be your slug flow. So you can just look at this scheme here. If you have this kind of flow, obviously it's not good for your flotation, any of this basically. So what we wanted was this flow, bubbly flow. And how can we get this thing? So we need to play with the value of JG, that is superficial gas velocity. And if you look at this picture, I think we are quite close to this. And where we are getting this one, that is a superficial gas velocity of 1 centimeter per second. And that's this value. So after this, we conducted all our experiments at superficial gas velocity of 1 centimeter per second. Yeah, at 1 centimeter per second, bubble diameter versus salt or further type shows that if you don't use any salt, we have this value, and if we use magnesium chloride and individually like different type of salts, how are they going to, what is their effect and how much is their effect on the bubble size reduction. And here the value that I showed you last time, like the high concentration of sodium chloride, if you use it, can almost mimic the further effect as well. And if you potentially see here, what we conclude from this is that we have conducted first part of our study, and we see that okay, the salt addition to our system is basically good for our flotation, so it's not affecting our flotation performance. So then we need to go some other way around. So that would be next part of our study. But still, to make sure how these salts react at different pH. So this study, I chose these two different salts, magnesium chloride and calcium chloride, because they are the one which are not affecting our bubble size quite much. So I just chose these two, and then I performed study at different pH, at pH 8 and 9.5, 10 and at 11, to see that how it behaves. And it was seen that okay, even regardless of the pH, it will stay the same. So pH has no effect on both gas holdup and average bubble diameter. And yeah, so this is our next part of the study, because what we concluded from the first part, that the salinity is not affecting our bubble interaction quite much, I mean adversely. Of course, it's promoting flotation. So there is some other thing that is happening in the back end, so we need to go for that. So then we said that okay, how this water salinity is affecting the adsorption mechanism of dodecyl amine on quart surface through microflotation and through contact amendments and through zeta potential. So when you use Hallimond tube for microflotation, and I think you always need to go and select the appropriate concentration of your collector. So here I'm using the 4 different concentrations of my collector. So 10 is for -6 molar DDA to 10 is for -3 molar DDA, and I'm seeing the recovery of quartz. So what I see that if I use a very high concentration of my collector, that is 10 is for -3 molar in this case, I'm almost recovering everything. So I cannot basically investigate how like my change in the salt or how my salt addition is going to change the quartz recovery. And same for 10 is for -6 molar DDA. I'm not recovering anything, like it's almost very less. So what I like, and if you look at 10 is for -5 molar DDA and -4 molar DDA, you see that at different pH values, you can see that at different pH values you can at least compare the results by the addition of salts. At very basic pH, at around 11.5, an interesting thing was observed. we have at 8 pH we have a very high recovery, then getting down, 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 and all of a sudden it drops at very basic pH at 11.5. Why that? Because if you look at the speciation diagram of amines, so the formation of RNH2, which is basically in the form of solids, that takes place at the basic pH. So which is why we are saying that once we cross 9.5 pH, so we start reducing our recovery. So once you have RNH2 precipitation on your quart surface, so regardless of very good conditions of flotation, you keep introducing your collector, and because you already have a precipitation of RNH2 which is positive, so your collector is not affect on that. So that's why you get a very poor recovery here. However, on the other hand, at ESN like phenol, so if you look at this pH 8, we saw very interesting results that we were getting quite good recovery of quartz at this range. So why not to take that into consideration? So as I said, like we chose firstly like 10 raised to power minus 4 molar DDA, and at 3 different pH recovery was then noticed, and these are basically legends, so each number corresponds to a different legend. And so what I am doing is first with the no salt and then adding salts individually and then making the probable mixtures, calcium, magnesium, and with potassium chloride, and then with sulfates, because anything could happen when you are dealing with the chemistry. You never know that what kind of reaction exists inside too. So to see that, I want to mix them all together as well and to see their effect. So it was seen that at pH of 8, regardless of the salt type or the mixture you use, you have always like a very high recovery. However, if you are working at a pH range of 9.5 and 10.5, which is basically the range at where cationic reverse flotation is performed, or any kind of direct flotation performed by the iron ore is 10.5, so you see that the salt additions reduces your recovery. It goes ups, downs based on the type of the salt. But yeah, from the results you could get an idea like the major contributors are calcium chloride and magnesium chloride together, and yeah, when you use like even the mixture sodium chloride and similarly sodium sulfate all together with calcium chloride and magnesium chloride. At 10.5 molar DDA, at all the pH values, yeah, the collector was not that strong enough, and we saw that if we have 10 raised to power minus 5 molar concentration of the collector, so what we see that yeah, by adding salts and their mixture, recovery drops down, and yeah, after the addition of calcium chloride and magnesium chloride together, we see like recovery is almost getting closer to 0. Well, here quartz recovery as a function of potassium chloride, sodium chloride, and sodium chloride is 2 times here, so probably it's some other salt type. Sodium sulfate, this should be sodium sulfate. It was seen at 10 raised to power minus 4 molar concentration, we don't see any significant drop in recovery. However, when we are using like the minus 5 molar DDA concentration to see that how each type of salt is affecting individually to my recovery of quartz, we see that sodium chloride is the one that affects my recovery significantly. So why is that all happening? We have kind of mixed effects sometimes. Sodium, in our previous study we see that sodium is promoting bubble like flotation in bubble interaction case, but then when we come across the surface studies of charges, and when we see that what is happening, like here it's sodium chloride is affecting adversely. So why is that happening? So first we would say that calcium and magnesium ions, why they affect our quartz recovery. So if you look at the speciation diagram, we see that at the basic pH, that is around like 10 or more. So we start forming, like if you extend it back, it would be somewhere landing at 9.5 pH or something. So we see that we have a formation of calcium hydroxide, and then at the extreme basic pH, you also start forming like calcium hydroxide in the solid form. And similarly, if you look at for the magnesium hydroxide, you see that at pH 8 and more, 8.5, you start the formation of magnesium hydroxide. So of course these are positive charges, so you have a silica surface. So when you have the hydrolyzed solution, so these hydroxides go and sits on the surface of silica and then prevents flotation even if you add a cationic collector. Why sodium? There is a very good diagram that's taken from the literature that you have a silica and surface charge, negative surface charge. When you have high concentration of sodium, they flood the surface of silica. Similar to that, they flood the surface of silica, and when you will add cationic collector, it will come, and this is positive, so of course they will not be reacting the same way when they react to the negative. So it will avoid the interaction of collector with the silica surface. And why sulfate? How sulfate, presence of SO4 ion affect your silica recovery? At a basic pH, it is seen like if you have calcium chloride, sodium sulfate in your aqueous solution, so what happens, you have very strong reaction of calcium sulfate in the solid form, and that sits on your silica surface. And alongside, it gives you sodium chloride as well. That is also adversely affecting your flotation, so it prevents your flotation of recovery of silica. Yeah, so a design of experiment was planned. So this is basically a model recovery, which is based on 36 experiments from microflotation. These 36 experiments include each salt individually and their possible combinations, which can affect your quartz recovery. And this is what I got, like this was the actual recovery that I performed in the lab by performing the 36 experiments, and then I got this model using JMP software. It gave me this model. So this model is basically a model that can give you a recovery based on the presence of your salts upfront at a lab scale, to have an idea that, okay, if you have, let's say in my case, my concentration I gave like lower and upper bounds, so the minimum salt presence of my magnesium chloride could be 0 and the maximum could be 0.01. That was based on my process water compositions, all this value. So staying inside that, this model can tell you the recovery upfront. However, you need to scale it up when you are going for pilot scale and industrial scale, because these are just results from microflotation. And it also shows you that you have a log worth value. So log worth, it basically shows you the significance of your parameter, which in this case are different type of salts. How significant are they in your results? I mean, like my output was recovery. So the role that magnesium chloride is playing is significant in comparison to the rest. And similarly, calcium is following that with less effect, and so on and so on. And I kept my predicted p value. What is p value? It is basically showing you, because in statistics you have a cumulative density function, and to work for any quartile or quantile. So what happens, like you pick a value for probability that corresponds to particular inside the distribution. To these p values are basically the area under the curves at the extremes. It could be like the left tail or it could be the right tail. I mean, in this case, my lower bound and upper bound. And I said, like the lower the p value, the more accurate you would be. So the more close you would be to your actual recovery. So I had very long table of that with different kind of combinations, but I restricted my p value to 0.0001. And then I got these 5 different type of combinations which affect my recovery, and the rest are all screened out. And here you can see the corresponding measures of error as well. It's not working. Yeah, so heading towards the contact angle measurements. So first I will tell you like what is contact angle. Contact angle basically tells you about the hydrophobicity of your minerals, that how much hydrophobic they are or how much hydrophilic they are. So the greater the contact angle, the more hydrophobic your surface would be, and vice versa. So again, those two concentrations of collectors, 10⁻⁴ and 10⁻⁵. I'm saying that these are the same legends which I used in the previous experiments. That my contact angle for the quartz surface at pH of 8 is like quite constant. It's quite high. I mean, it's close to 70 degrees, regardless of the type of salt or the combination that I am using at this concentration. So it means that my surface is behaving hydrophobic at this concentration of GDA and at a pH of 8. But on the other hand, if you work at a typical pH of the cationic reverse flotation, that is pH 10.5, what we see is that it reduces as you keep on adding different type of salts with each other. And at 10⁻⁵, of course, always low. So it gave us another clue, because at pH 8 we are getting interesting results, that we are getting a very good recovery. We are getting high values of contact angle measurements. So there is something interesting happening in the back end at pH of 8. So we further investigated that to another study, which is surface charge measurements through zeta potential. So zeta potential is basically the surface charge measurement, as I told you, at different pH. I studied that at acidic, at somewhere like around a natural pH range, that is around 8 to 9, and yeah, at the basic pH range where like the cationic reverse flotation is performed. So when you have no salt, or if you are operating at the acidic pH or somewhere close to natural pH, you see that you have a negative pH. I mean, your surface of silica is still behaving negative. So when you would be adding your collector, so it would be going straight and attacking on the silica surface and then floating it. But it's quite interesting to see here that what is happening when you keep on adding different type of salts and their combinations. So we are moving the charge from negative towards positive, and a point comes, that is this red point, where you have like combination of all of them, all the different type of salts. We literally changed the surface charge of silica. That goes positive. And yeah, if it goes positive, it means like your surface needs then anionic collector, not a cationic collector, so it doesn't float it anymore. So which is why process water salinity is affecting the recovery of quartz at basic pH. So as I told you, like at pH of 8, so that is basically the normal pH of the natural pH, that is between 8 and 9. We were seeing some interesting results. So why not to perform our flotation at this pH range? If we have to use process water, no one ever tried this thing before. Like, yeah, what if you shift the pH down to normal pH? You can get like very efficient results on that, and you will then be able to reuse your process water. So which you saw like happening from all these different type of fundamental studies, through contact angle measurements to zeta potential measurements for microflotation. Yeah, so yeah, you would have seen that I was just working on pure silica, and I was investigating its recovery, and I never did like any real flotation, advanced flotation. But here is the flotation that was done before my project came in at the research center, and they saw that they used the real ore from the side, and like the real water then they used also. And they performed some experiments, bank scale flotation, using process water, using different type of collectors, and they saw that they were not able to isolate silica if they used process water from the site. So if you look at here, they are using Lilafloat F2A35, so they cannot even reduce. So silica is still somewhere close to 8%, and same for another ETA and K2C. It's somewhere close to 4. It's still unacceptable. However, if you use a meth tap water, so you are able to reduce that to 2%. And yeah, here they use different type of collectors. So here it is like a natural pH that's not an 8 to 9, and similarly the same. So they use different type of that, and they are using processed water. And they also investigated that, well, if they use natural pH and they use the same kind of collectors in a processed water, so they can significantly reduce silica. So it means that now we have bank scale flotation, now we have fundamental studies, now we have column scale flotation. That's a pilot test, and we have microflotation, and yeah, zero potential and contacting measurements. All these supporting studies can conclude that why not to go for natural pH if you have processed water and perform your flotation, and you would be contributing somehow to the scarcity of water that is quite potential to be happening in the future. So the conclusions of the presence of salts in the processed water reduce the average bubble size and restrict pollutions. Yeah, calcium and magnesium are mainly responsible for poor quartz recovery at a basic pH due to the formation of calcium hydroxide and magnesium hydroxides. And presence of sulfates prevents amines adsorption at quartz surface due to the formation of calcium sulfate. And the sodium high concentration also inhibit quartz floatability at pH 10.5 when your collector concentration is less than or equal to 10 to the power minus 4 molar. And the presence of salts in processed water changes the surface charge of the minerals, which quartz in this case, thereby affects the flotation recovery, as you saw, because we shifted the charge to positive. High salinity effect on quartz flotation can be reduced by performing flotation at pH of 8 to 8.5. A predictive model can be used to estimate the effect of processed water salinity on the silica recovery. A cost-effective and eco-friendly solution of potential water scarcity issue to be faced by the mining industry, particularly treating iron ores. Yeah, that's all. Thank you very much for your attention.